So far, we have looked at objects that are moving back and forth in a straight line, one-dimensional kinematics. Now that we have seen many examples of solving puzzles in one dimension, we shall expand out to puzzles in 2 dimensions. The techniques of solving 2-dimensional kinematics puzzles are largely identical to those for solving one-dimensional kinematics. That's because the motion in the x direction in 2D is entirely independent of the motion in the y direction. The variables are largely separate, which means that a 2-dimensional puzzle is more or less just 2 one-dimensional puzzles that have to be solved one after the other. Consider this puzzle. A plane is oriented toward east. Its initial velocity is 40 meters per second, and it is accelerating at 0.5 meters per second squared. However, there is a strong wind pushing it northwards at a constant 15 meters per second. What is its displacement after 30 seconds relative to its starting point? To solve this, we will draw a picture to represent the fact that the plane is flying east but being pushed north. We will take 2 photos, and we will set origin and axes. We'll apply our familiar kinematics variables, but we have to do this in x and y separately. The only thing that is common to both directions is the time. So we draw a table like this. In x, we have displacement, initial and final velocity, and acceleration. And we have corresponding quantities in y. Now, what was the unknown in this question? What is the displacement of the plane? The displacement. But be careful. The plane was moving in x, but the wind was pushing it in y. So both displacements are unknown. What is known? The initial velocity of the plane is 40 I hat meters per second. Its acceleration is 0.5 I hat meters per second. The initial velocity of the wind is 15 j hat meters per second, and the acceleration of the wind is 0. The time is 30 seconds. In the x direction, we are looking for displacement, and we know initial velocity, acceleration, and time. The only toolbox equation that relates all these values is number 2. We substitute the knowns and solve for the displacement. It is 1,425 I hat meters. In the y direction, we are again looking for displacement, and we know initial velocity, acceleration, and time. Again, we use toolbox equation number 2. We substitute the knowns and solve for the displacement. It is 450 j hat meters. So the overall displacement is 1,425 I hat plus 450 j hat meters. In other words, after 30 seconds of flight in the wind, the plane is located 1,425 meters to the east and 450 meters to the north of its original point. Notice that this is a vector in Cartesian notation. We can convert this into polar notation. We use the Pythagorean theorem to find the displacement. It is 1,496.36 meters. And we use the arctangent of y over x to find the angle of displacement. It is 17.53 degrees. So, we can equivalently say that after 30 seconds, the plane is located 1,494.36 meters from its starting point at an angle of 17.53 degrees. And although the puzzle didn't ask for it, we could solve for the final velocity in photo 2. In the x direction, the velocity of the plane is 55 I hat meters per second. And in the y direction, it remains 15 j hat meters per second because there was no acceleration. The classic 2D kinematics puzzle is the motion of a projectile. Whenever something is moving horizontally but still falling under the influence of gravity, it is experiencing projectile motion. Projectile motion plays a huge role in sports like tennis, football, golf, basketball, and so forth. For our purposes, we will look at a cannonball. Consider this situation. A cannon is at the edge of a 15-meter cliff. It is aimed horizontally. It fires a cannonball at 40 meters per second. Solve for the cannonball's A, time of flight, and B, range. We'll start by drawing a picture. Photo 1 will correspond to where the cannonball was launched and photo 2 to where it lands. We will set the origin as the launch point and the axes such that rightwards is positive x and downwards is positive y. We were asked for the time of flight, so the time is unknown. The second part of the question asks for the range of the cannonball. Range simply means how far away the cannonball lands. It is a synonym for horizontal displacement, the displacement in x. We are told that the vertical distance through which the cannonball falls is positive 15 j hat meters. We also know that it was fired horizontally. That means it had no velocity in the y direction initially, but its velocity in x was 40 meters per second. Finally, the acceleration in y is due to gravity, 9.81 meters per second squared. And unless you are told otherwise, in projectile motion, acceleration in x is always 0. In the y direction, we're looking for time. We know displacement, initial velocity, and acceleration. So we can easily use the second toolbox equation to solve for time. You could use the quadratic formula if you really wanted, but this one is easy enough that you don't have to. You get a time of 1.75 seconds. That's how long it takes for the cannonball to land. If we had tried to solve for the displacement in x first, we would have gotten stuck, because we had only 2 pieces of information in x. But by using the y direction to solve for time first, we now have 3 pieces of information in x. Again, time is always consistent between x and y. It represents the time between the 2 photos. In x, we are looking for the displacement, and we have horizontal velocity, acceleration, and now time. So we can use toolbox equation 2 to solve for the displacement. It is 69.95 I hat meters. We've now solved the puzzle, but while we're at it, we can also find the final velocity in both directions at the landing point. In the y direction, we can use equation 3 to find the final velocity. It is 17.16 j hat meters per second. and in the x direction we can use equation 1 to find its final velocity. It is 40 I hat meters per second. But here, finding the final velocity in x is pretty trivial. Since the acceleration is 0, the final and initial velocities must be the same. You probably noticed that the calculations we did in the y direction are very similar to the calculations we've already seen for freefall. That's because the cannonball is indeed undergoing freefall in y. It just has an additional independent motion in the x direction tacked on. Here is another type of question that can be asked with respect to projectile motion. A cannon is at the edge of a 10-meter cliff. It is aimed horizontally. The cannonball lands 30 meters away. What was the cannonball's initial velocity? We begin this question the same way we begin any other question, by drawing a picture. I'm going to add in a couple of extra details. The height of the cliff is 10 meters, and the vertical displacement, or rather the horizontal displacement, of the cannonball is 30 meters. Let's set photo 1 as being the initial position of this cannonball, and photo 2 as its final position. So rightwards as the positive x-axis, and downwards as the positive y-axis. The question asked, what is the launch velocity of the cannonball? That's vi in the x direction. Now, let's list all the information we know. The displacement in x is 30 meters. The displacement in y is 10 meters. The cannonball was launched horizontally, so the initial velocity of the cannonball in y is 0. The final velocities are not known, but the acceleration in x is 0, and the acceleration in y is positive 9.81. So here's how we would go about solving this. We have 3 pieces of information in y, but we're looking for something which is in x. Whenever you're given this sort of situation, you need to find a linchpin between them, and that linchpin is the time. With 3 pieces of information in y, you solve for the time. You now have 3 pieces of information in x, and you can solve for the initial velocity in x. Let's try it out. In the y direction, we know displacement, initial velocity, acceleration, and we're looking for time. The only equation which weaves together these 4 quantities is equation 2. So delta y is equal to v initial times t plus 1/2 a t squared. So delta y is equal to 10 is equal to v initial times t plus 1/2 9.81 times t squared. 0 times t will cancel out. So we're left with 10 is equal to half times 9.81 is 4.905 t squared. So t squared is equal to 10 divided by 4.905, which is about 2.02. Take the square root of both sides, and you'll end up with t is equal to 1.43 seconds. So we have now solved for the time of flight of the cannonball. Now we have 3 pieces of information in x, and we're looking for the initial velocity. The only equation that weaves together displacement, initial velocity, acceleration, and time is once again equation 2. So delta x is now equal to v initial times t plus 1/2 acceleration times t squared. So displacement 30 is equal to v initial, unknown, times t, 1.43 seconds, plus 1/2 times the acceleration times t squared. But half times 0 is going to be 0 and the whole second term will just cancel out. So we are left with v initial. We can divide both sides by 1.43. It's going to be equal to 30 divided by 1.43, which is equal to 21.01. And if you want to be really rigorous about it, we would say 21.01 I hat meters per second. So this is the launch velocity of the cannonball. In this video, we were introduced to two-dimensional kinematics, and we saw its most important application, projectile motion. And what we see is that two-dimensional kinematics is really no different from one-dimensional kinematics. It's just that we have to do the question twice. In the next video, we will see some more applications of projectile motion, including what happens when that cannon is angled.